Yes, so let us continue solving the questions, the tutorial problems. So in this question you can see a uniform plane wave is given and it is traveling in air and it is normally incident on an infinite lossless dielectric material. So an infinite lossless dielectric material is here like this, and on this material, okay, maybe so this is the boundary and you have this infinite lossless dielectric medium, and on it a wave is hitting normally like this plane wave, and the properties of this medium, and this is air. So in air we assume that mu r and epsilon r is equal to 1, and in this case the epsilon is given as 3 times of epsilon naught, implying epsilon r equal to 3, and mu is equal to mu naught, implying mu r is equal to 1. So the incident wave is given, so the incident wave expression is given as 10 times of cos of omega t minus z ay cap. So what I can see from here is, because it's a wave going is incident normally, and this is a wave, from this factor it looks like the standard format 10 times of cos of omega t or some e naught, some electric field magnitude cos of omega t minus beta z. It looks in this format. So from this equation what I can tell is the wave, so the wave, this is your field direction, and this gives your wave direction. So the wave direction is positive z direction, so the wave is going along positive z axis, and I can see that from this beta is equal to 1, and the magnitude of electric field is E naught is 10. So I can convert this expression in phasor format, so that is to say that EI can be written as, of course let us do that afterwards, but first of all uh, the question asks for what is lambda and omega of the wave in air and the transmitted wave in the dielectric medium. So the question asks for what is the frequency here and what is the frequency here, and what is the wavelength here and what is the wavelength here. If we assume this is first and second region, so they are asking what is this. Obviously, because the source decides the frequency, omega 1 should be equal to omega 2, which is equal to omega. So we have this expression that the velocity of the wave, right, the velocity of the wave is given by omega divided by beta. So in our scenario, this is an incident wave, so you have beta 1 here and you have beta 2 here. So what we have here is beta 1 is equal to 1, implying that this is actually the incident wave. So this is in the first region, so beta 1 is given as 1. So the velocity in the first region for this electromagnetic wave should be equal to beta 1 times of omega. But we know, because it's in air we can say the velocity is 3 into 10 to the power of 8, and because beta is 1, so from here you have omega. So the omega value is I can say it is 0.3 gigahertz or 300 megahertz. And what is the value of wavelength here? So we need to calculate the value of wavelength. Okay, so let me calculate the value of wavelength. So I can see that the same omega goes in all places. So what is the value of wavelength? So, but of course here also the expression should be valid. I can also say that v2 should be is equal to omega divided by b2. Okay, or from here I can say beta 2 is equal to omega divided by the velocity v2. Right, so what is the velocity in the second medium? The second medium, the velocity is given by c divided by square root of epsilon r2 times mu r2. So we have epsilon r2 and epsilon r1 here, I mean epsilon r2 here. If you substitute it, we get that this is equal to, so this is equal to 3 into 10 to the power of 8 divided by root 3, right? So I can see that from I can replace this v2 with 3 into 10 to the power of 8 divided by root 3, and of course this value here is 3 into 10 to the power of 8. That gives me that beta 2 is actually is equal to root 3 radians per meter. Okay, so I have the value of beta 1 and I have the value of beta 2. So once I have the values of this beta, then finding the wavelength is simple, because beta is always equal to 2 pi by lambda. So if it is beta 1, this is lambda 1. If you have beta 2, that is 2 pi by lambda 2. So from here I can say, implying that lambda 1 is nothing but 2 pi divided by, so let me erase this expression here, 2 pi divided by beta 1, which is equal to 2 pi, whereas lambda 2 is 2 pi divided by beta 2, which is 2 pi divided by root 3, right? So this much meters is your wavelength in both regions for this. So this is for the transmitted wave and this is for the incident wave. Alright, so we have the equations, means we have calculated the value of lambda and omega for both the incident and transmitted waves. So let us go with the next one. We need to calculate the incident magnetic field. So let me write the electric field in phasor form, means this part can be written as a real part of 10 times of e power j omega t into e power minus j times of z ay cap, right? So if you want the phasor format for this, so the phasor format is like this. So you neglect the real part and e power j omega t, so you'll be left with 10 e power minus jz times ay cap. So I can see that the wave direction, so the wave direction is positive z direction. So your electric field and magnetic field should cross product your directions, gives you the wave direction. So because the magnetic field, electric field is in ay cap direction, to give you a magnetic field it should be in minus ax cap direction. So that means if I want to write the incident magnetic field, it should be e power something here and the direction. So we had the direction now, so let me write the direction here, that is ax cap, right? Because any field we usually have to fill these three blanks. So what about the magnitude? We know that the magnitude of electric field divided by the magnitude of the field should be is equal to the intrinsic impedance eta naught. So the magnitude of this one is nothing but magnitude of electric field divided by eta naught. And what about this factor? So because it is a wave, because it is incident wave, so electric and magnetic field should have the same phase, e power minus j factor, right? So this is your incident electric field. So now the other part of the question asks for what is a reflection coefficient. So reflection coefficient, because it's a normal incidence, so it is eta 2 minus eta 1 divided by eta 2 plus eta 1. So let us try to pull the values of this eta 1 and eta 2. So in the first case, eta 1 is nothing but square root of mu naught by epsilon naught, which is nothing but eta naught. But in the second medium, okay, it is square root of mu divided by epsilon, that is square root of mu r2 divided by epsilon r2 into mu naught divided by epsilon naught. So that is 1 by root 3 times eta naught, because epsilon r is 3 and mu r1 is 1, mu r2 is 1. So if I substitute these values, I basically end up with 1 by root 3 minus 1 divided by 1 by root 3 plus 1. So which is nothing but eta naught. I mean, so you get into eta naught in the numerator and denominator get cancels out. So you have 1 minus root 3 divided by 1 plus root 3. So this is your reflection coefficient. So if you ask me what is a transmission coefficient, so the transmission coefficient for the normal incidence, the transmission coefficient formula is like this: 2 times of eta 2 divided by eta 2 plus eta 1. So I can say it is 2 divided by root 3 divided by 1 by root 3 plus 1. So I can say this tends to 2 divided by 1 plus root 3. So this is your transmission coefficient, and you have your reflection coefficient. So I think the third part of the question is done. So the next part of the question is to calculate the total electric field and the time average power in both regions. So this is interesting. Previously we have solved a question where the wave was hitting a perfect electric conductor and we saw that the average power went to 0. So let us do this. So let me write the incident electric field. So in order to calculate the total field, means total electric field and the time average, we need to calculate the fields in both regions, right? So let me rewrite these equations here so that we can be on track. So let me write the transmission coefficient. We had 2 by 1 plus root 3, and we have the reflection coefficient as 1 minus root 3 by 1 plus root 3. Okay, right. So let me write the incident wave. So the incident wave in phasor format was like this: e power minus j times of z ay cap, and the magnetic field expression was like 10 divided by eta naught e power minus jz times minus ax cap. So this was your incident electric field. So what I want now is the reflected waves. So the reflected field is the reflection coefficient times the incident electric field. That part is only for the magnitude. We were seeing this from long back by solving the problems. So first of all, you need to fill these things. So right now we're not worried about the direction, so we'll write it as ay cap here. And what about the magnitude? The magnitude will be reflection coefficient times the incident electric field. So that is 10. So this is your magnitude. And what about the factor here? Because the reflected wave, incident wave is coming like this, the reflected wave will be propagating in opposite direction. So you will definitely get plus j times of z. Okay, so because you get the same, so in both cases, here in this case beta 1 is 1, here in this case also beta 1 is 1. So you need to write, actually here we need to write j times of beta 1 times of z because it's in the first medium. Okay, but we know that beta 1 is 1, we have calculated previously. So I wrote it as j times into z. So this is your incident electric field. So the question is, what is a magnetic field? So the reflected magnetic field is what you get from the wave. So because the wave is now traveling in negative z direction, okay, and in order to satisfy E cross H, if this is in AY, then this should be in AX. So here you get an AX cap, and of course here you get same plus JZ, and here you have the magnitude divided by eta naught because it's the first medium. So this is all reflected wave. So let us talk about the transmitted wave. So to get the transmitted, so because the transmitted wave will be traveling in positive z direction, I can see that I just have to fill these 3 boxes, and let me assume that the direction is, we're not going to change AY cap. And what about this here? So here, because the transmitted wave is traveling in the second medium, and here the propagation constant was root 3, right? So if it is root 3, then what you will get in this numerator? So you need to write minus of j beta times of z, beta 2 times of z. Why? Because it's a wave traveling in positive z direction. So this is your transmitted and this is your reflected and this is your incident wave. So because it's traveling in positive z direction, definitely you get a minus j beta 2 times of z. But what is beta 2? Beta 2 is nothing but equal to root 3. And what about the magnitude of the field? The magnitude of the field is nothing but the transmission coefficient times the incident wave 10. So we have the expressions, right? For the reflection coefficient, we have 1 minus root 3 divided by 1 plus root 3, and for the transmission coefficient, we calculated it as 2 divided by 1 plus root 3. So let us put them aside. So now if we ask me what is the magnetic field expression, okay? So the magnetic field expression is nothing but tau by 10 divided by eta naught into e power minus j root 3z into the direction, because it's a wave traveling in positive z direction, you get minus ax cap. Right? So you have the fields, all kinds of fields. So if you ask me what is the total electric field, the total electric field is ei bar plus er bar in the first region, whereas in the second region the field is er and hr, right? In the same way, h bar is hi bar plus hr bar. So because I want to calculate the power here, so the time average power in the first region is half times of, let me call this 1 and 1. Okay, half times of, I'm sorry, here I have this is the convention here, so it is transmitted fields, right? ET, or we call them as the fields in the second region. So I can say the power in the first region is half times of real part of the total field cross H conjugate for the total field, right? So if I do that, so let me write the expressions for the incident electric field. So the incident electric field expression is like this. I have incident electric field, the total incident electric field E1 bar as 10 times of e power minus jz plus tau times of 10 e power plus jz times ay cap. So this is your E1 field, whereas your magnetic field H1 is like this, 10 by eta naught e power minus jz with a minus sign plus tau into 10 divided by eta naught into e power plus jz, this whole thing times ax cap. So now, because I need a conjugate here, wherever there is a j, you replace it with plus with a minus sign, right? Minus with a plus sign. So this is what we get. So I have to take cross product between these two. You can see the cross product between ay and ax is nothing but ay and ax. You get minus az. Okay. So when you do the cross product, you will be left with minus az, and you have to multiply these two factors here. So if I multiply these two factors, I get 10 into minus 10 by eta naught plus tau times of 10 square divided by eta naught. I think it's a big expression, let me write it. And after that you have minus, sorry, there is into e power minus 2jz, okay, plus, I mean you get a minus again, minus 10 by 10 square by eta naught into the reflection coefficient into e power plus 2jz, and the last term is tau square. I'm sorry, I made a mistake here. Tau can also be a complex number, so you get a tau conjugate here. So you get tau into tau, you get tau modulus of tau square. So you get modulus of tau square into 10 square divided by eta naught. So this is what you get when you multiply these two factors, and into you have minus this whole thing into, because it has a direction. Let me write the direction here. It is minus az cap. So this is your factor. So for this whole factor you need to take the real part of it. So if you do the real part, so let me erase few things here so that we can get an answer. So if I erase this factor here, so if I take a real part, what I can see here is there are real numbers in this expression and complex numbers here. You can see if I have an e power minus j and e power plus j, e power j terms, these becomes complex imaginary numbers, and these also contribute to imaginary numbers, right? Oh, of course, you might say it might not be imaginary because e power minus 2jz, or say, okay, fine, maybe we'll do it like this. So you can take this tau into this factor common here in these two equations. If I write it so I'm having a scenario here like this: half times of a real part of minus az cap times minus 100 divided by eta naught plus reflection coefficient square into 100 divided by eta naught, okay, plus reflection coefficient into 100 square 100 divided by eta naught times e power minus 2jz minus e power plus 2jz. Okay, so this is what I have, and I have to take the real part of it. So if you can see this equation, this expression is nothing but I can say it is 2j times of sine 2z. Okay, so because sine 2z can be written as e power plus j 2z minus e power minus j 2z divided by 2j. Okay, I think you have a reverse, so you get a minus sign here. Okay, so I can erase this thing and I can simply write it here, this factor. I can say it is minus 2j times of sine 2z. So you can see that because I'm taking a real part here, okay, minus 2j sine 2z. Okay, so because I'm taking a real part here and this number is an imaginary number, right? Imaginary number. So whatever the real part is, this is your real part. So if I take only the real part, I am left with half times of minus of minus, it goes to plus. I can say that this is 100 by eta naught, okay, minus reflection coefficient square into 100 by eta naught. Okay, so if I take this 2 also inside, it is divided by 2 eta naught, or this I can write it as 100 by 2 eta naught into 1 minus reflection coefficient square, which is a very interesting result. So let me put these results aside and after that we'll talk about it. But this is the result which we got. Okay, so this is the total time average power in the first region. So in the first region there is an incident wave and there is a reflected wave. So this is the total time average power which I get. So let me write this thing somewhere so that we don't lose it. So let me write here, there is some empty space. So in the first region we have the time average power as 100 by 2 eta naught 1 minus modulus of tau whole square. So let me erase this thing here. So let us do for the second region. So in the second region, I need to calculate the power, time average power. So in the second region there is only one field. Okay, so I can write it as half times of real part of E2 cross producted with H2 bar, H2 conjugate. So here if I take conjugate to this, what happens? If I take, let me write the fields. So E2 field in our case is tau times of 10 into e power minus j root 3 z into ay cap. But if you ask me what is H2, H2 is tau times of 10 divided by eta naught into e power minus j root 3 z times minus ax cap. I think I have somewhere here in all these equations I've forgotten to write az cap here. Basically it's a vector. So this is az cap, it's a vector. Okay, so this is the means this says there is a finite. Okay, we'll talk about what are the interpretations after calculating all the values. So this is your if I take conjugate to this, I have, so in the second region, actually I think I have made a mistake while writing the field in the second region. In the second region the intrinsic impedance is not eta naught. We saw that eta 2 is actually eta naught divided by root 3. So here you need to take eta 2, sorry my bad, and eta 2 is actually eta naught divided by root 3, so you get a root 3 in the numerator. So I think you get a root 3 in the numerator, and this is eta naught. So if I take conjugate, you get transmission coefficient conjugate, and e power minus becomes plus. Now if I multiply these things, so if I want E cross product between this magnetic field and the conjugate of it, what do I get? What is the answer I get? Is you can see that if I take the when I take cross product, ay cross minus ax simply gives you az, and if I multiply tau and tau conjugate, you get modulus of tau square, transmission coefficient square. 10 into 10 gives you 100 divided by eta naught into root 3, and this into this gives you e power 0. Okay, and this you have to take real part of s and you have to multiply with half. Basically this is whole thing is a real number, so I can say this is nothing but modulus of tau square divided by 100 into 100 times of root 3 by 2 eta naught. Or if I rearrange it a bit interestingly, I can say this is root 3 times of 100 divided by 2 eta naught. Okay, so this is your time average power in the second region. In the second region, this is your time average power. Right, so let me summarize my results here. Okay, so I'll erase all these things and I'll summarize my results. So I can see that in the first region, the average power is like this. So time average power was like 100 divided by 2 eta naught times I think 1 minus you got modulus of the reflection coefficient square. And in the second region we got the time average power as 100 divided by 2 eta naught times root 3 into modulus of transmission coefficient square, and we have the values for the reflection coefficient as root 3 1 minus root 3 divided by 1 plus root 3, and for the transmission coefficient you have 2 divided by 1 plus root 3. Of course you can substitute those values here and you can get the answer, but one thing that is very interesting here to see is this one. So what you can observe here is, what is this factor here? Basically 100 into this factor. If you observe it, of course the direction is az cap in both cases. I can say that in both cases there is a power that is flowing in z direction, even with the reflection. So there is an incident wave and there is a backward wave. So forward wave undi, backward wave undi. But the net effect is like there is still some amount of power flow in the positive z direction. If you remember in one problem where we had a perfect electric conductor and there is an incident wave and there is a backward wave, there is no power flowing in z direction because whatever power is coming in is reflected back. But here there is some amount of energy that is transmitted into the second region. So definitely, so there is a time average power that is flowing into the z direction. And what is that value? We can see that the electric field magnitude is 10. So because it's a uniform plane wave, we know that the power, the time average power that is carried by the incident wave is nothing but magnitude of this electric field square divided by 2 eta naught. So you can see that is nothing but 100 divided by 2 eta naught. So that is what we have. So this part is nothing but the average power of your incident wave, and this is your average power of your incident wave. So I can see that the time average power of the transmitted wave is nothing but incident power into root 3 into the transmission coefficient, whereas the time average power of the incident wave, I mean so the total energy or the total power in the first region is nothing but the power that is incident. So this I can write it as power that is incident minus power that is reflected back, right? So az cap, I can say this part is nothing but the power that is reflected back. So you can see that whether because if you subtract, because there are no losses from the incident power, if some power is reflected back, the remaining power should be traveling to the transmitted power, right? So what I want to check is whether these two entities are equal. They should be, because whatever power is incident and some power is reflected back, the remaining power should be the transmitted power. So on a time average that should happen. So let me see that whether 1 minus modulus of tau square is equal to root 3 times of modulus of this square. Okay, so if I want, this is 1 minus I can say it is 1 minus root 3 whole square divided by 1 plus root 3 whole square is equal to root 3 times of the tau value is 2, is you get a 4 divided by 1 plus root 3 whole square. So if I do it, I have 1 plus root 3 whole square by, okay, so I can get this cancels out. So this looks like a square minus b square. Sorry, I mean this is a plus b whole square minus a minus b whole square. So you will be left with 2 times of a into b, that is 1 into root 3, I mean 2 times of 2 times of a into b, that is you get 4 times of a into b. So you get 4 times of a is 1, b is root 3. That is what you have on the other side also. So you can see that it actually holds. So whatever power is coming in, as part of the power is reflected back and the remaining part is transmitted, and in fact that is what you see in your answers when you calculate the total average power for the total fields in both first region and second region, right? So we'll move on to the next problem. Okay, so let me, right, so if you see at this question, the wave is traveling from a dielectric medium and it is incident upon air boundary. So if this is your region, okay, so I can see that z equal to 0 is your plane. So z equal to 0 is your boundary, and the second region is air, and the first region is some dielectric medium with the following parameters: 9 epsilon naught and mu naught, whereas this is epsilon naught and mu naught. Okay, and I can see that the value of the wave is in xz plane, but anyways, let us try to figure it out. So because the interface is z equal to 0 boundary, the normal to the interface, so I'll choose this as z axis. Okay, and because the wave is traveling in a xz plane, I choose this as x. Okay, so now let us try to find what is the incident wave vector. So I'm assuming that the wave is coming like this, but let me check whether the wave is coming from the down or whether it is coming from the up. So how do you decide? So whether the wave is coming like this or is coming from the down, it depends upon your k bar vector. So if your k bar vector have both a positive z component and a negative x component, then maybe the wave is coming like this. But if your if your k bar vector is like this, then you can see you have both positive x component and positive z component for your ki bar vector. So let me check what happens. So here the magnetic field expression is given, but whether it's magnetic field or electric field, this is the incident wave. So the incident wave, if I try to write it in phasor format, so I get zero point 0.2 times of e power minus j times of kx plus k root 8 z times ay cap, right? So what I have done here, because you can always write that as 0.2 real part of e power j times of 10 to the power of 90 into e power j minus of kx plus k root 8 z into ay cap, right? So here you neglect real part and 10 to the power of e power j omega t, that is when you get the phasor format, right? So we have the phasor format now. So this is your phasor format expression for the magnetic field. So if I know the magnetic field, I can see that the wave direction is given by this factor, because Ka bar dot r bar is actually here kx plus k root 8 z. So this implies that incident vector Ka bar is k times of ax cap plus k root 8 times of az cap. Okay, so that gives me that the vector is positive, both positive and positive z component, x and z component. So in fact the wave is coming from the bottom like this. So this is my Ka bar vector. So I have the magnetic field here. So what is the electric field is what I want. Okay, so to calculate the electric field, there are two ways to calculate it. Okay, so let me go with the first way, that is the electric field, incident electric field, because we have this equation like del cross of hi bar is equal to j omega mu times, sorry, j omega epsilon times dou d by dou t, means I mean j omega epsilon times electric field, right? So all you have to do is you have to take the curl of your magnetic field, so that gives you ax ay, so dou by dou x, dou by dou y 0, and you have y component as 0.2 into e power minus j kx plus k root 8 z, and of course you have az component dou by dou z and 0. So let me try to calculate the det of it. So the det of it is, I can see that I get ax times of minus of dou by dou z of the 0.2, this factor. So if you take a derivative of it, you get the z component, that is k root 8. Okay, k root 8 into 0.2 into e power minus j kx plus k root 8 z. Okay, that is one thing. You have the x component, and then y component is 0, and for the z component I can see that az cap, for the z component you have dou by dou x. So with respect to x you have to take the derivative. So you have minus j. I think I forgot another minus sign here in the x derivative. So when you are taking x derivative you get a minus sign here, and when you take the derivative with dou by dou z you get minus of minus. So let me put a minus sign here. You get minus and minus of this factor. Okay, I think there is j also. I forgot the j. Okay, so if I write that here also derivative with x is minus jk into whatever factor you have remaining. So you get kx plus k root 8 z. So this is your curl. Okay, then if you divide it by j omega, so you have to divide this whole equation with j omega epsilon. So what is omega? So here omega, I can say omega here is nothing but, because the magnitude of k bar should be equal to the propagation constant we have in the first medium. Okay, and I can see that the omega here, so this becomes beta, and I can say that should be equal to, in the first region, what is the velocity of the wave in the first region is omega divided by beta, which is nothing but 1 by square root of mu into epsilon, that is divided by 1 by square root of mu naught epsilon naught. I think I don't have place here, so I will write it as 1 by square root of mu naught epsilon naught square root of mu r1 and epsilon r1. So 1 by square root of mu naught epsilon naught is nothing but c divided by square root of mu r, and mu r is 9, square root of 9. So you can see that this is nothing but c by 3. So the velocity is c by 3, then the frequency omega is nothing but c by 3 times of beta 1. So what is beta 1? If I take the magnitude of this, I can see that the magnitude of it is k square plus k square into 8 of whole square root. So you get 3 times of k. Okay, so if it is 3k, so this is basically 3 into k. So that means omega is simply c into k. Right, we have omega here, so omega is c into k. And what is epsilon? Epsilon is, because it's in the first medium, epsilon naught into epsilon r1, that is 8.85 into 10 to the power of minus 12 into epsilon r1 is given as 9. So this is omega epsilon. So you just have to divide this thing, this whole factor, by j omega epsilon. Okay, if you do that you'll end up with this thing. You'll end up with the electric field, incident electric field. So here you can see the j cancels out in all the equations. So here j cancels out, here also j cancels out, minus into minus simply becomes plus. So I get plus k here. Okay, there is still minus sign here. So j got cancelled out. Now you have left with omega epsilon. So if you divide it by omega epsilon, then I get the answer for the, I have omega, which is 3 into 10 to the power of 8 into k. So if you given substitute it, so you get 3 into 10 to the power of 8, and of course the k factor also gets cancels out. Okay, and you have 3 into 10 to the power of 8 into 9 into 8.85 into 10 to the power of minus 12. So I think you get 10 to the power of 4 minus 4. So this is how you get. So if you divide it, then you get the electric field answer. So this is one way of calculating the electric field. let me use another way to calculate the electric field here. So the incident electric field. Oh, I think the omega is given here, right? So the omega is given as 10 to the power of 9. That is good. But anyways, we still have the same answer, not an issue. Okay. So what about, so from here I think I can actually calculate the value of k, because I got omega is nothing but c into k. Okay, I can say, so if I put 10 to the power of 9 here, so 3 into 10 to the power of 8 should be equal to k, implying that k is equal to uh, 10 divided by 3. So I got the answer for k. So k value is equal to 10 divided by 3. And I have the incident angle. So if you want the incident angle, so okay, before doing all those things, I've said there is another way in which you can calculate the incident electric field. So let me do it. So because the magnetic field is actually in y direction, which is coming out of the board. Okay, so you can see that. So this is the direction of your magnetic field, and this is your wave direction. So in order to have your wave in this direction, because E cross H should produce, right, it should produce the wave direction, your electric field should be in this direction. Okay, your incident electric field should be in this direction. You can always divide this component into two parts like this, and I can see that if this becomes theta I, this becomes 90 minus theta I, so this becomes, or this becomes 90 minus theta I, that implying this becomes theta I. So if this is theta I, then the opposite component is sine component, so this is sine theta I, and the same side component is cos theta I component. Okay, so if I, so I get this answer like, so what I can do is, so because I have the, how do I write the electric field here? So you can write the electric field like something like this. So your electric field is nothing but something into e power minus j something into the direction of the field. Right, so the direction of the field, I can see that there is cos theta component, cos theta I component in x direction, and minus sine theta negative z direction, so it is minus sine theta I in az cap direction. And what about this k bar dot r bar? We have already this k bar, so it is simply k times of x plus k root 8 times of z. So this is, the other blank is to find the magnitude of it. I know that the magnitude of electric field to the magnitude of magnetic field should be equal to the intrinsic impedance of the first medium. So what is the intrinsic impedance of the first medium? So for the first medium, let us try to calculate the intrinsic impedance. So the intrinsic impedance of the first medium is square root of mu naught divided by epsilon naught into square root of mu r2 divided by epsilon r2, which is nothing but eta naught divided by 3. Whereas eta 1 is nothing but square root of mu naught by epsilon naught, which is eta naught. Okay. So from here I can say that because the magnitude of electric field is nothing but intrinsic impedance times the magnitude of the magnetic field, so I can write the magnitude of the magnetic field as 0.2. So it is 0.2 times of eta 1, or it is 0.2 times of eta naught divided by 3. So that is your expression for electric field. So that is one way of calculating the expression for your electric field. Okay, so let me write the expression so that I can use it. So in the same way, I can also calculate the expressions for the transmitted and reflected electric fields also. So let us do that. But before doing that, how do I write? So first I need to calculate what is a theta r, that is angle of reflection, and what is the transmitted angle theta t. So to get that, we can write theta I is equal to theta r. And what is theta I? Theta is the angle, incident angle. So I can see the normal vector is z-axis. So what is the angle you make with z-axis? So I can say that it is nothing but the vector k bar is making an angle, how much angle it is making with z-axis. And I take this product, dot product, right? If I do that, I get k root 8 divided by the magnitude of it is k 3k. Okay, so k gets cancels out, it gives you a root 8 divided by 3. So that is cos theta I. So if this is cos theta I, from here I can calculate the angle of incidence as, so let me use my, so I'm getting it around 19.471 degrees. Okay, so if cos theta is this thing, so how do you get the transmitted angle? So you get beta 1 sine theta I should be is equal to beta 2 sine theta t. So beta 1 is nothing but omega square root of mu naught epsilon naught square root of mu r1 and epsilon r1 sine theta I is equal to omega square root of mu naught epsilon naught square root of mu r1, I mean mu r2 epsilon r2 times sine theta t. So because mu r2 and epsilon r t is here, so it is 1, and you can see this factor cancels out with this factor, and mu r2 and epsilon r2 substitute, if you substitute them, you basically get a 3. Square root of 9 is 3. So I can say 3 times of sine theta I is equal to sine theta t. So what is the value of sine theta I? So we have the angle. So let us put that angle and try to find it. So if you put sine theta I, you get something around 1 by 3. Okay, you get something 0.333, or you get it around 1 by 3. So which is nothing but sine theta t. That means theta t is what? 90 degrees. So this is basically the critical angle. So the wave is hitting exactly at the critical angle. So that is why your theta t is 90 degrees. But anyways, you still have a, it's not beyond the critical angle. So it is exactly hitting at the critical angle. So you have a theta t which is 90 degrees. Okay. You can check this one also. Right, you can see we can also get whether I'm right, right, sine square theta I is 1 minus cos square of it, it is 8 by 9. You can see that it is 1 by 9, so sine theta I is nothing but 1 by 3. So it cancels out perfectly, so give you theta t which is 90 degrees. So the wave is making an angle, so there is a reflected wave definitely, but there is transmitted wave is like this, it is creeping on the x-axis, right? So that is your transmitted wave. So I have theta t as 90 degrees. That makes things very interesting. So now let us try to calculate what is the reflected electric field. First we'll calculate the reflected electric field. After that we'll calculate the uh, I mean probably the transmitted electric field. So what is the reflected electric field? So in any case the reflected electric field expression looks like this. So the reflected electric field is some magnitude and e power minus j is kr bar dot r bar and the direction. Okay. So I can see that this is my reflected wave. So what is the value of kr bar vector? So kr bar vector is nothing but beta 1 times of cos phi x into ax cap plus beta 2 times of cos phi y into ay cap plus beta 1 only, beta 1 times of cos phi z into az cap. So I can see that the reflected wave, so because this is also theta I, the reflected wave is making an angle of 90 minus theta I with x-axis. So it is the phi x is nothing but 90 minus theta I. So you get beta 1 times of sine theta I ax cap, and of course with y-axis, because y-axis is perpendicular to this plane, it makes is 90 degrees, so cos 90 is 0, and beta 1 times of because with respect to z-axis it is making an angle of 180 minus theta I, so you get minus of cos theta I times az cap. So this is your reflected wave bar vector. So I have the values of sine theta and cos theta, right? So where are they? So in the where is it then? So cos theta I think I got something like root 8 by 3. Yeah, root 8 by 3. And sine theta I got it as 1 by 3 if you remember. And what is the value of beta 1? So beta 1, I had the value for beta 1 also, I think probably somewhere, I think here we had omega as c into k, or let me write beta. So it is beta 1 is nothing but omega times of square root of mu naught epsilon naught into square root of mu r1 and mu r2, that is 9, that is 3, and this value square root of omega times of square root of mu naught epsilon naught, so we had the value of omega which is 10 to the power of 9, and square root of epsilon naught by mu naught is 1 by 3 into 10 to the power of 8. So I can see that 3 gets cancels out and I have 10. Okay, so I have 10, or I can also say this is 3k. You get it is exactly equal to 3k. So if I put this value here, 3k, so I can see that 3 gets cancels out and I get kr bar dot r bar something like this. You have only k in x direction minus root 8 times of k in z direction. So that is your reflected wave kr bar dot r bar. Now what about the direction? So I can see that the wave is going back like this, and because the magnetic field we assume that it is coming out of the board, so in order to have a wave direction like this, okay, E cross H should point in the wave direction. So your magnetic field is coming out of the board. So if you have your electric field like this, then E cross H will be pointing in outward direction. If I do that, I can basically divide this into two components, one which is like this and another one which is like this. And I can see that if this angle is theta I, this becomes 90 minus theta I, making this angle as theta I. If this is theta I, the opposite component should be sine component. So this is sine theta I component, and this component should be cos theta I component on the same side. So I can see that there is cos theta I in negative z direction, so it is minus cos theta I in negative x direction, and you have positive, you also have interestingly a negative uh, component of z. Okay, you have minus sin theta I in az cap direction. So this is your direction of their electric field. So what about the reflected electric field? So the reflected electric field is nothing but the reflection coefficient into the incident electric field magnitude. So the incident electric field magnitude was like this, mu naught divided by 3. So that becomes your magnitude. So the reflection coefficient is what we have to calculate here. So the reflection coefficient, what kind of polarization it is? I can see that the electric field is parallel to the plane of incidence. So it is a parallel polarization. So the answer becomes like eta 2 uh, cos theta t minus eta 1 cos theta I divided by eta 2 cos theta t plus eta 1 cos theta I. So I can see that when I put theta t as 90 degrees, these values go to 0, and I left with minus cos theta by diamond, so which is nothing but minus 1. So I can see that the parallel polarization, the reflection coefficient is simply minus 1, nothing else. So if I put here with a minus 1, then I get the final answer, right? So this is the expression for the reflected electric field. What about the transmitted electric field? So if you have to write the transmitted electric field, you go in the same way. So if you want the transmitted electric field, let us try to get that one too. So the procedure is always same. You can always work with the knowledge here. And the problem is the transmitted electric field. First let us try to calculate what is the transmission coefficient. So the transmission coefficient is like 2 times of eta 2 times of cos theta I divided by 2 times of not 2, eta 2 cos theta t divide plus eta 1 cos, so this is for parallel polarization, right? So cos theta I. Okay, so in this, if I put theta t as 90 degrees, this factor goes to 0, and I'm left with 2 times of because theta get cancels out, it is 2 times of eta 2 by eta 1. So what is eta 2? You can see that eta 2 is eta naught, so this is 2 times of eta naught divided by eta naught by 3. So which is nothing but 6 eta naught by 3, so you get a value of 6. So that is your transmission coefficient. But here interestingly, what about the electric field? What about the electric field, transmitted electric field? So if your vector was not on the z-axis, if say for example if your transmitted electric field was like this, then you might have written, if this is your theta t, then you might have written your kt bar as something like this, beta 2 times of right, cos theta x and all. Okay, and if you calculate what is the value of beta 2 here, so beta 2 is nothing but omega times of square root of mu naught epsilon naught into square root of mu r1, and epsilon r1 is 1, so that is beta 2. So omega is 10 to the power of 9, and square root of mu r epsilon r is 1 by 3 into 10 to the power of 8. So this is basically 10 by 3. So I can say your beta 2 is exactly 10 by 3, or I can say it is equal to k. So I can put here k times of, so you can see with x-axis you're making an angle of 90 minus theta t, so you get sine theta t. Okay, and ax cap plus, because with z-axis you're making an angle, with y-axis it is 90, so this goes to 0, whereas with z-axis it is making an angle of theta t, so you get beta 2 times, which is k, times cos theta t times az cap. But if you put theta t as 90 degrees here, you can see that in that scenario this goes to 0 and this goes to 1, so you basically have kx cap. You can see that is what is happening. So your kt bar is basically kAx cap. Okay, so if that is a scenario, how do I write the transmitted magnet electric field is nothing but something into e power minus j times of kt bar dot r bar with the direction of the magnetic field. Okay, so because I know that the magnetic field is pointing in y direction like this, so in order to have a wave that is traveling in x direction, I can say that the electric field can have component in what direction. So because if the magnetic field is coming out of the board, then if you have E in this direction, you can see that E cross of H will not give you the wave direction, so your electric field should be pointing in this direction. Okay, because your magnetic field is coming out of the board. So if that is a scenario, okay, if your electric field is in this opposite direction, I can say that the electric field is basically in negative z direction. Okay, so I have the component minus az cap, and now the kt bar dot r bar is what, because kt bar is simply kx, so it is k times of x. Okay, and what is a transmitted component? So it is nothing but the incident the transmission coefficient into the magnitude of your incident wave, right? So what is the magnitude of your incident wave? So we had that is 0.2 eta naught divided by 3, so you put the transmission coefficient, which is 6 here. So if I do that, I can see that this becomes 2, which is 0.4, so this becomes 0.4 times of this. So this is your expression for the transmitted field. So this wave is basically moving on the x-axis, right? It's on the surface, so it is the reflected wave, means the transmitted wave is on the surface, it is creeping on the surface, because you basically you had the incidence angle exactly at the critical angle. Okay, of course if you go beyond the critical angle, you have evanescent waves in the second region also. Okay, but right now you don't have any evanescent fields also. Okay, so this is the uh, transmitted and the reflected electric fields. So what about the Brewster angle? So because this polarization is parallel polarization, okay, so this is a parallel polarized wave. So for parallel polarization, the Brewster angle, because the mediums have this mu r1 and mu r2 are both equal to 1. Okay, so the Brewster angle, simply because they are dielectric mediums, so the Brewster angle simply becomes tan inverse of square root of epsilon r2 divided by epsilon r1. So that is tan inverse of square root of epsilon r2 is 1, and whereas epsilon r1 is 9. So I can see that it is tan inverse of 1 by 3. Okay, so the angle basically is 1 divided by 3, so it is 18.43 degrees. Okay, so if you incident at this angle, okay, if you are incidenting at this angle, this whole wave will be completely transmitted, so there will not be any reflection. Okay, but you went beyond the Brewster angle, and in fact you have chosen exactly the critical angle. So we saw the above conditions.